Okay. Now, let us come back and study the next higher homologue of cyclopentane, that is cyclohexane, which is actually the most interesting and most well studied of all these cyclic systems. Now, we have seen that this puckering of these rings started from cyclobutane, and why the puckering takes place? The simple reason is to reduce the torsional strain. Okay. In case of cyclobutane, although the angle strain increased a little bit, but the gain is more if you reduce the torsional strain. In cyclopentane, there is virtually angle strain is virtually 0. So, even if you make it puckered, the angle strain still remains 0, but you gain much more because you are reducing the torsional strain. Now, let us come to the cyclohexane. Okay. Now, cyclohexane according to Bayer should be planar. Okay. If you try to make it planar, you see it's very difficult. You cannot really straight away make it planar because it's so flexible, it's very difficult. But suppose I force it and make it a planar molecule. So, this is the planar molecule of still it is moving, it is very difficult. But if you try to make it planar, you see the angle starts little bit bending. I do not know whether it is visible there. The angle bends a little bit because it will suffer from angle strain, because the angles will be then 120 degree, but the normal angle is 109 degree. So, this little bending, I hope actually it is very difficult to hold it in that fashion. I will try again. Yes, it does not, that means it is not stable. If it does not want to remain in this fashion, it is not stable. So, you see the bending now, the top one you can see the bending a little bit. Okay. So, what happens? You have the angle strain in the planar form, and in addition you have huge number of torsional strain, because there are now adjacent bonds increases, the vicinal carbons relationships, number of relationships between the vicinal carbons, that increases. So, you have very large number of torsional strain. So, to avoid that, cyclohexane adopts what is called adopts some conformations, non-planar conformations, again puckered conformations, where the angle strain is 0, angle strain is perfectly maintained at 109 degree 28, means correct is 109.28 minutes, but for approximation we can say 109.5 degrees. Okay. So, the valence angles are perfectly maintained, and but still it is puckered. First there is Sachse and Mohr, I think Sachse and Mohr, they first predicted that cyclohexane exists in two extreme conformations. They identified two conformations for cyclohexanes, and one of them is called a chair conformation. Okay. So, this is one conformation which is called a chair conformation. Okay. Why chair conformation? Because it looks like a chair. So, if you look at this molecule, so you see that there is a leg of the chair, then this is the handle arm of the chair, and this is the where you rest your head. Okay. So, this looks like a chair. So, this is called a chair form of cyclohexane. Sachse and Mohr also identified another one, which is called the boat conformation. This is what is called a boat conformation. This is, you see, this is very flexible. So, that is why I could get to these conformations very easily. So, this is the chair conformation, again I show, and this is the boat conformation. Okay. So, these two they identified. Now, how to draw the chair and the boat conformations of cyclohexane? I can draw it quite quickly because I have done it up to number of times. So, first draw the chair conformation, and this is the chair form, and this is the boat conformation. Okay. Now, between these two conformations, it has been found that cyclohexane exists mostly in the chair conformation, and there are reasons for which board conformation is quite unstable, and we can discuss that later. However, there is another form which is in between the chair and the board, and that is what is called twist board form. We will come back to this later. This twist board form has lower energy than the board form, but has higher energy than the chair form. And it is true that most of the cyclohexane molecule exists mostly in the chair conformation. And let us inspect the chair conformation, as this is the principal conformation that cyclohexane exists. The first thing that is important in chair form while drawing this, see, there are some students draw in a very bad way like this chair. So, there are certain rules in drawing this chair form or certain architectural pattern that this chair form follows. Okay. And what is this? So, we have to identify that what are the important criteria or important points architectural, from architectural point of view, okay, or geometric point of view. What are the criteria that it satisfies? Okay. This is the chair form again. We put some number, carbon numbering, that will help 1, 2, 3, 4, 5 and 6. Okay. So, in this you see this carbon is above this carbon, that is very clear. So, if you start from this carbon, C4 carbon, so these two bonds is going above, is going upward direction. Okay. Then these two bonds, the next two bonds, they again now they come in the downward direction, and then after that again these two bonds approach in an upward direction and finally meet at this point. Okay. So, what happens now? You have 3 upward points. These 3 are the upward points, because these bonds are going up and these bonds are also going up, and you have 3 downward points. 3 downward points. Let us see whether we can use different chalks. So, these are the 3 downward points. Okay. So, what happens here? This C1, C3 and C5, C1, C3 and C5, they lie in one plane, and C4, difficult to draw here, but C4, C2 and C6, they lie in another plane. Okay. We can come back to this geometry, to this model, and then show it. So, what I am saying, that there are 3 top carbons, which are these 3. So, they lie in one plane, and there are 3 bottom carbons, which are these 3, one, this one, that one. See, they alternate each other. This is alternating. So, the back carbon, a bottom carbon, not back, a bottom carbon, then a top carbon, then bottom, then top, then bottom, then top. Okay. So, it alternates. So, 3 top carbons lie in one plane and 3 bottom carbons lie in another plane, and these 2 planes are parallel to each other. Okay. So, there is an average plane. I can say that there is an average plane which is going through the middle of these 2 planes. Okay. So, that is the first thing. And the second thing is now, what about the bonds at the carbons, because you have this carbon carbon framework, but now you have, in addition, you have the hydrogens. You have the hydrogens. So, if you look at the model, you see, or do not look at the model, before we go to the model, let us try to do it in the board, because as I said, models are good, but you do not always have the facility of this molecular model system. So, it is better to try to visualize the thing. So, when there is a carbon at the top, you see that there is a one bond which goes vertically upward, okay, and another bond which is here, which is downward, but it is not vertically downward. It is, I have drawn it in such a way that this is parallel to these bonds. So, this is parallel to this bond or that bond. In fact, these two bonds are parallel to each other. That is also a beauty of the chair system. These bonds and these bonds are parallel to each other, and then this one and this one are parallel to each other. So, which bonds are parallel? Just the internal framework C1, C2 is parallel to C4, C5, parallel to each other, and then C1, C6 is parallel to C3, C4. So, they are parallel, this means parallel, and then C5, C6 is parallel to C5, C6 is parallel to C2, C3, they are parallel to each other. So, while drawing the chair form, you have to maintain this parallel relationship between these bonds. You have to maintain while drawing this. Okay. I will show you how to draw a chair form for beginners, because sometimes, as I said, many people draw it in a deformed form, which is not correct. So, there are some ways to draw it correctly. Now, the question of these bonds, the outside bonds of the cyclohexane. So, there is a bond which is, if it is top carbon, so there are 3 top carbons C1, C5 and C3. So, one bond will be vertically upwards and the other bonds will be parallel to the next adjacent carbon-carbon bond. So, this bond will be parallel to the next adjacent carbon-carbon bond, and in the bottom carbon you have now, instead of going upwards, you again have vertical bonds like this. Again you have vertical bonds like this. This is the bottom carbon and this is the bottom carbon. So, you have a vertical bond like this. So, again vertical bonds are there, but bottom carbon the vertical bonds go downwards and the upward carbon the vertical bonds go upwards. Okay. And what about the other bonds in the bottom carbon? Because in the top carbon, what I said, this is parallel to the next adjacent carbon-carbon bond, the same thing happens here also. So, when you draw the fourth ligand here, that should be parallel to the next carbon-carbon bond, next carbon-carbon bond, next means next adjacent. So, this one or this one. So, this should be parallel to this. Okay. So, if I try to draw the bond here, the fourth ligand, that should be parallel to this and this. Okay. If I want to draw the fourth ligand here, that should be parallel to this and this. Now, sometimes people ask that this parallel line I can also add in this direction. This is also parallel to this. So, what is wrong with this? The wrong is that it cannot, actually all these 3 bonds cannot be in the same direction on this side. So, one bond has to come in this position. You remember the sawhorse projection formula. So, what happens? This is the kind of sawhorse projection formula. So, you cannot have a sawhorse projection formula where this is there. This is in the sawhorse, it is not possible. Okay. So, that is why there is no bond in this direction, although this is parallel to this bond. Okay. So, it is parallel, but going in the opposite direction. This is parallel, but going in the opposite direction. This goes from here to there, this goes from here to the opposite direction. So, we have identified how to draw the inward bonds. The inward bonds, as I said, these are parallel to each other, and outward, the outside, the bonds, the outside bond, that means which are not making the ring. So, outside the outward bonds, they are, we have identified some vertical and some vertical bonds like this, and some bonds which are parallel to the next adjacent carbon-carbon bond. Okay. Now, there are other points which we need to remember, that is, we have said that there is a plane here C1, C5, C1, C3, C5 lies in one plane, and this plane, if it is a reference plane, then this bond is above that plane, above the plane containing C1, C3, C5. So, according to the nomenclature conventional, that nomenclature system, this is beta bond, okay, and this bond is below this plane containing C1, C3, C5. So, that must be alpha. Okay. So, this is a beta bond and this is an alpha bond. So, if we come to the next carbon C2, now this belongs to the carbon which is lying at the bottom plane. So, C2, C6 and C4, they form another plane. Here you see this is above that plane. So, this should be beta and that should be alpha, okay. And it actually this vertical bond here, it is beta, the next vertical bond is alpha, the following vertical bond is again beta, the next vertical bond is again alpha. So, it alternates, then it comes to beta and this is alpha. Okay. So, that means this is how the alpha beta relationship between the bonds are designated. Okay. This is designated as per the plane that the carbons belong to. Okay. The top carbons have a plane and the bottom carbons, they lie in a plane, and these alpha beta are basically the whether these bonds are above those planes or below those planes. Okay. This is important while drawing the cis trans derivatives, disubstituted derivatives of cyclohexane. That is important, because what is cis, as I said, alpha alpha or beta beta will make a cis relationship and alpha beta or beta alpha will make a trans relationship. Okay. Now, these bonds, apart from this designation of this alpha beta, they have some other names. Okay. These vertical bonds are called axial bonds. So, this is what is also called an axial bond. This is also an axial bond. Okay. And the other bonds, see, one thing is very interesting, that these axial bond is perpendicular to the plane containing these 3 carbons. So, it is just orthogonal to that plane. However, this is going down, but it is not orthogonal to this plane. It is lying little bit closer to that plane. I can go to the model. See, if I take the model, so you can see this is the bottom carbon. So, this is going downwards, vertically downwards. So, that is the axial bond, and this bond is the equatorial bond. This is going upwards, but it is not that far away from the bond, from the plane that I am talking about. This carbon, that carbon and these carbons are the bottom carbons, that makes a plane. So, this is little bit above that plane, it is beta, but the point I want to emphasize is that this is going far away from this plane, but this is slightly above the plane. So, these are called equatorial bonds, because if you think this is as a kind of a circle, if you put a circle here, a plane containing a circle. So, these bonds lie close to the circle. So, the equatorial concept came from that if you have this our mother earth. So, what happens, this is the kind of say the equatorial the equator. So, the things which lie close to the equator are called the equatorial bonds. Okay. See, you can always say bonds which are not axial, they are equatorial, but that is not the correct way of saying. You should know the origin of equatorial bonds, because it lies equatorial. Basically what happens is that if you consider this as a circle, now a circular plane. So, these bonds lie close to the circular plane, the plane of that circle, rather than these bonds. These are actually going, these are orthogonal to that plane. So, they are called axial and this is equatorial. Now, why these are called, this is equatorial we understand, because it is closer to this the plane, if I think it is a circular plane. So, they are called equatorial, but why it is called axial? It could have been called vertical bonds, but we do not call it vertical bonds, okay? We call it axial bonds. So, what is the definition of axial bond? Now, you can say bonds which are vertical to each other, vertical, these bonds, the bonds are all vertical, axial bonds are all vertical. Okay. So, you can define it as that vertical bonds are axial and the other bonds are equatorial. You can also tell that bonds which are mutually parallel to each other, this bond is parallel to this bond, see all these bonds are parallel to each other here, the axial bonds. So, bonds which are mutually parallel to each other, they are axial bonds. That is another way of looking at it. However, the question is what is the origin? Means like equatorial name has a origin because it is close to the equatorial plane of the cyclohexane system. Axial must have why it is called axial bonds, they must have a origin, the name originated from something else, that is why it is called axial bonds. And if you say that bonds which are vertical they are axial bonds, that is not correct, because if you hold the chair form, in this fashion, then the definition changes. Bonds which are horizontal, that becomes axial bonds. See, these are axial bonds, the way you hold the chair, that is important. So, you cannot say that bonds which are vertical they are axial bonds. So, that is the wrong concept, because it is then you have to say I have to hold the chair in such a fashion that these bonds look horizontal at this vertical. Okay. So, that is not the correct definition. The correct definition is that, which also tells that why it is called axial, is that this is a cyclohexane, remember all these are hydrogen. So, I removed those two bonds. So, this is cyclohexane. So, in cyclohexane, if you rotate this, if you think there is an axis here and you start rotating this cyclohexane along the axis. So, what you see that if I do a 60-degree rotation, again I go back to the earlier one. Earlier the head of the chair was on my left side, okay, and on the right side is the leg of the chair, the bottom of the chair. If I do a 60-degree rotation, the whole thing changes. The bottom of the chair is now on my left side and the topmost position, the head of the chair is now on my right side. So, the appearance changes, appearance of the chair changes. Now, if you give further 60-degree rotation, then what happens? Then again we come back to the original position. The head of the chair is to my left and the bottom of the chair is to my right, which was my starting point. So, basically what I did a rotation of first 60-degree, but I did not come to the same position, same appearance, but then I made another 60-degree rotation. So, it appeared the same like the earlier one, the starting point. So, that means it has got what is called 360 by 120. So, that gives you a number 3. So, it has got a C3 axis of symmetry, C3 simple axis of symmetry. Okay. C means simple axis of symmetry. So, that simple axis of symmetry is here. If I rotate the chair in this fashion, the simple axis of symmetry will go through this. Okay. It is still there, but it changes the way if you orient the chair in this fashion, then the simple axis of symmetry will go through this point, it will be inclined. Okay. But what remains constant is that these bonds, the axial bonds, remain parallel to this simple axis of symmetry. So, the simple axis of symmetry goes through this point and it will always be, the bonds will always be, the axial bonds will always be parallel to this. So, that is basically the other way to say is that they are coaxial with this simple axis of symmetry. So, that is why they are called axial. So, they have originated from the coaxiality of these bonds with the C3 axis. Okay. So, that is why. So, now what we learned, that there are, first of all, cyclohexane exists mostly in the chair form. As I will come back to the half chair later on when we do the energy profile analysis, but right now concentrate on the chair form. That is the most common form, most stable form. We have identified two types of bonds at the carbons. You can define it in two ways, either axial equatorial or you can say beta alpha. So, there are two ways of descriptors. One is axial. So, what is the axial bonds? Bonds which are coaxial with C3, because it has got a C3 axis. Okay. So, that is the correct definition of axial bonds, and the bonds which are very close, which are lying almost in the equatorial plane, that is called the equatorial bonds. So, these concepts are very important. We will just end up with one more concept, but next class will definitely will elaborate that issue. The issue is that this chair form, like pseudo rotation, I have told you already in cyclopentane, that the bond all in cyclobutane also, that the bonds which are up they go down, the bonds which are down they go up. That is happening all the time. In chair form also very similar thing happens. The bottom of the chair can go up and the head of the chair can go down. So, this is again, that is what is now in this case it is called flipping. It is very similar to pseudo rotation, but we have a special term here, the chair flips. Chair flips because, why flipping? Because the head of the chair becomes the bottom of the chair and the bottom of the chair becomes the head of the chair. Okay. So, this is the, I again show the process of flipping, that the bottom of the chair goes up and the head of the chair goes down. Okay. And what happens? The chair looks like looks little bit different. Earlier it was looking like this, now it will look like a mirror image of this, because this goes down and this goes up. Okay. So, if we follow this numbering, that means this is 1, that is 2, that is 3, that is 4, that is 5, that is 6. Okay. So, this is what is called flipping of chair, and it is, there is a sign for flipping, and that sign is that you have to put a kind of half circle here. See, you know a lot of, this means 1 electron movement, this means 2 electron movement, this means equilibrium, this means resonance, and now you have another type of arrows, and that is that you, when you put these circles here on the arrow, half arrows, that means flipping, that means this is now flipped and go into this form. Okay. So, next we will discuss that what happens to the axial equatorial bonds, what happens to the beta and alpha nature in the chair form when it flips from one to the other, and then what happens to the energy associated with it, because that is what we have discussed in butane, that when you rotate, what happens to the energy. In this case, this is also a kind of rotation, flipping is also a kind of rotation. So, when you flip, what happens to the energy, how does it vary when you go from one chair to the mirror image chair, that is called the flip form. So, that is one aspect. Another is what happens to the axial equatorial bonds and what happens to the alpha and beta nature of the bonds. Okay. That will be in the next class. Thank you.